Hilbert curves, an ivyOptic presentation. This presentation showcases original topological transformations and insights into space-filling geometry. Goals are to demonstrate the untapped potential of space-filling curves, inspire innovations in storage optimization, and open doors to future collaborations. These are the topics that will be covered in this presentation. First, you'll learn what a Hilbert curve is, and then we'll delve into some more fascinating subjects of what can be done with the curve by transforming its topology. A Hilbert curve is a 1D line that fills the space of a 2D regular square. This video has been provided by 3 blue, 1 brown. An order 1 Hilbert curve fills the space of a 2 by 2 square grid. An order 2 Hilbert curve fills the space of a 4 by 4 square grid. And an order 3 Hilbert curve fills the space of an 8 by 8 square grid. Hilbert curves pass through the center of each square in their grid. An order 1 Hilbert curve passes through each quadrant, starting at the bottom left, moving to the top left, then the top right, and finishing at the bottom right. This process repeats for higher order curves. If we take 4 order 1 Hilbert curves and tile them to a grid, rotate the first one clockwise 90 degrees and the last one counterclockwise 90 degrees, and then add these green connectors, we get an order 2 Hilbert curve. If we tile 4 order 2 Hilbert curves to a grid, rotate the first one clockwise 90 degrees and the last one counterclockwise 90 degrees, add these green connectors, we get an order 3 Hilbert curve. An order 3 Hilbert curve can be subdivided into 4 order 2 Hilbert curves or 16 order 1 Hilbert curves. And on to a new discovery, Hilbert curve negative branch fractals. A 1D line has no thickness, thus it cannot fill the space of a 2D square. Hilbert curves only fill space when expanded. In red is the minimum of a Hilbert curve, a 1D line, and in purple are the expansions of a Hilbert curve that fill 2D space. In white is the order 2 Hilbert curve minimum. This purple outlines a half-expanded order 2 Hilbert curve, which is halfway between the minimum and the maximum expanded. If we remove the border and fill the gaps, we get order 1 negative branch fractals in green and order 2 negative branch fractals in blue. In white is a minimum order 3 Hilbert curve. Outlined in purple, we have the half expansion. If we remove the border and fill the gaps, we get order 1 negative branch fractals in green, order 2 negative branch fractals in blue, and an order 3 negative branch fractal in orange. Order 5 negative branch fractals. The curve itself in this diagram is black. The gaps between the curve form negative branch fractal patterns. Order 7 negative branch fractals. The curve in this diagram is black. Every color belongs to a negative branch fractal. Here we can see the cascading patterns embedded in the negative branch fractals. Tiling 4 order 2 Hilbert curves to a grid creates an order 3 Hilbert curve, raising the order by 1. Tiling 16 order 2 Hilbert curves to a grid creates an order 4 Hilbert curve, raising the order by 2. Tiling 64 order 2 Hilbert curves to a grid creates a looping Hilbert curve composed of order 2 Hilbert curves looping on a larger order 2 Hilbert curve. The beginning and end of a looping Hilbert curve make a full loop within the confines of the grid, filling each square. The orange and green sections connect at the beginning and end of the looping Hilbert curve. Now we can see the minimum expansion of the curve without the grid. To form a looping Hilbert curve, we multiply the order's square count by 8, then shrink the curve down to 1 over that total, and tile each curve seamlessly, connecting the two colored paths. And here we have half-expanded order 2 Hilbert curves, looping on an order 2 Hilbert curve. These are the negative branch fractals of order 2 Hilbert curves looping on an order 2 Hilbert curve. We can see the order 2 Hilbert curve in black, but now it has gained these additional black negative branch fractal appendages that fill a higher resolution of squares. Negative branch fractals in nature. Crown shyness occurs when trees leave small gaps between their outer branches. This creates a striking vein-like pattern in the forest canopy. Trees of the same species do this to reduce branch collisions in the wind, limit the spread of pests, and improve access to sunlight by not overshadowing each other. Water and electricity. The branching patterns you see on this board of wood are called Liptenberg figures. They form when a high voltage of electrical discharge courses through an insulated material along the path of least resistance. And here we have a topographical map. The mountain ridges are in black, and the gaps between the mountain ridges, painted in blue, form rain channels, which merge into streams and then rivers. The mountain ridges and the waterway channels are negative branch fractals of each other. There may be potential applications for Hilbert curve negative branch fractals in the storage or dispersal of energy, resources, or information. Hilbert time in the second dimension. Every square in this grid represents a still frame of time. These are daily pictures of a pinecone seed growing. The white line here is an order 3 Hilbert curve that passes through each frame, like a movie reel. A single square frame can represent an entire second-dimensional universe, and the next frame over can represent the next frame of the entire universe. The images here are sourced from Box Labs on YouTube. These animations and the speech of the first video are provided by 3 Blue, 1 Brown.
Increase the resolution of the camera's image from 256 by 256 to 512 by 512. If you were using the snake curve, as you transition to a higher resolution, many points on this frequency line would have to go to completely different parts of pixel space. For example, let's follow a point about halfway along the frequency line. It'll end up about halfway up the pixel space, no matter the resolution, but where it is left to right can differ wildly as you go from 256 up to 512. With the Hilbert curve technique, as you increase the order of a pseudo-Hilbert curve, a given point on the line moves around less and less. It just approaches a more specific point in space.
Mapping the pixels of a 2D image to a 1D line using a Hilbert curve preserves the general location of pixels when a Hilbert curve is scaled. Mapping photos chronologically along a 2D Hilbert curve ensures that events close in time retain proximity when the dataset gets scaled. In a traditional grid, chronology is mapped row by row. Adjusting the grid's scale changes where rows begin and end, causing photos that were adjacent in time to be separated across different parts of the screen. With the Hilbert curve, chronology is mapped onto a space-filling curve that preserves time-based locality across scales. The first diagram is a year in 16 images, arranged chronologically along an order 2 Hilbert curve. The 4 quadrants of the first curve represent summer, spring, fall, and winter. If we select the spring quadrant, the year or overall data set will get upscaled to a higher order curve, and the screen will display spring in 16 images arranged chronologically along an order 2 Hilbert curve. Selecting a quadrant of spring upscales the overall dataset to a higher order curve, and the screen will display a quarter of spring in 16 images, arranged chronologically along an order 2 Hilbert curve. The Hilbert photo album viewer allows users to locate specific moments based on context of events that occurred around the same time. Radiation, heat, light, sound. They all follow the inverse square law. A sonic boom is an invisible force field that carries particles at the speed of sound. As the field doubles in size, particles will spread over 4 times the surface area, lowering the density of particles on the field's surface to 1/4 the intensity. The geometry of sound is like a faucet dripping into a sink full of water. The center, where the water droplets land, continuously makes circumpunctual ripples on the water's surface. Imagine this ripple concept, but instead of circles on the surface of the water, it's spheres in space that expand continuously from their origin. Radiation is the proliferation of spheres. The edge of the sphere carries particles. The gaps between the spheres lacks particles. Waves are the measurement of particle density, and bipyramids can be used to represent the peaks and troughs of particle density. All forms of radiation follow the inverse square law, and the Hilbert curve has a direct correlation. This is orders 1 through 5 layered inside of the same square. If we start at the center of the grid and travel to the beginning of the order 1 Hilbert curve, we will have traveled a distance of square root 2. Traversal to the origin of the order 2 Hilbert curve will be the square root 2 divided by 2. Further traversal to the beginning of the order 3 Hilbert curve is the square root 2 divided by 4, then by 8, then by 16. The radius of each circle is twice as large as the previous, which means the surface area of each circle is 4 times the previous. This next video, provided by Henry Segerman, illustrates the developed Hilbert curve.
Hi, my name is Henry Segerman. This is Developing Hilbert Curve. So just as with Developing Dragon Curve, this shows the process by which the Hilbert curve is generated. So you start out with this curve consisting of 3 line segments. It's been smoothed out a little bit to make a nice surface. This time the next version of the curve is actually 2 steps down. You see the curve around here goes around like this. There's enough space to put in two steps of the windows and the surface in that time. So there's actually only 4 iterations of the Hilbert curve in this model. So here's the 4th version of the Hilbert curve. You see these 3 windows here with the bulge coming out is repeated here and then here as well. You see these same patterns repeating all over the place.
Developed Hilbert curve bipyramids, a derivative of Henry Segerman's study. Separate Hilbert curves by equal gaps. Connect each section with pyramidal extensions. These truncated pyramidal sections are also called frustums. By treating the base of each section as a frame, these frustums can be used to map particle positions over time. The density of the curve on each layer represents the density of particles. By tiling 6 of these pyramids to a cube, we can map a full 360-degree view of particle behavior. Mirror each pyramid by its base results in a rhombic dodecahedron, a bipyramidal extension of the cube. Pink is the origin, where particles are the least dense. It is also the trough of the wave. Orange is the peak of the wave, the surface of the sonic boom, where particles have the highest density. The developed Hilbert curve bipyramid. Bipyramidal radiation packets. The pink sections are the origin and the troughs of the wave, where particles are the least dense. The orange sections are the peaks of the waves. They are the surface of the sonic boom, where particles have the highest density. Hilbert radiation can be applied to more spherical shapes than just the cube. This is a diagram of a Hilbert curve being applied to a rhombic icosahedron. The Hilbert curve can be applied to any shape that has rhombic faces, Hilbert disks and cones. Emptiness is limitless potential. Here we have orders 1, 2, and 3 Hilbert curves mapped to a disk with the beginning and end meeting so that the Hilbert curve loops back onto itself. There are two ways to map a Hilbert curve to a disk. You can map it so that the beginning and end meet towards the inside, or that the beginning and end meet towards the outside. Below is a comparison of both diagrams. If you take a Hilbert curve disk with the beginning and end facing outward and place them inside of a Hilbert curve with the beginning and end facing inward, you can nest them inside of each other. The outward-facing Hilbert curve will have to be shrunk to a significant degree to fit inside of the inside-facing one, even further so for higher-order curves. Here we have two order 2 Hilbert curves connected at beginning and end. If we were to map these onto disks both and project them so that they were equal on a bicone, we would get a polar coordinates map of a Hilbert bicone where both disks are equally balanced. The Hilbert bicone, by extruding a disk into a cone and combining two of these cones together, you can result in a Hilbert bicone. This is an order 5 Hilbert bicone with the negative branch fractals, an order 7 Hilbert curve bicone, and an order 9 Hilbert bicone. This video features two order 9 Hilbert disks merged into a bicone. If you inflate a cone into a dome and merge two domes together, you get a sphere. And thus we have two order 9 Hilbert curves on the surface of a sphere. And this is a singular order 7 Hilbert curve mapped onto the surface of a sphere. Hilbert totems. There are multiple ways to fold a Hilbert curve to a rectangular prism. On the bottom here we have two squares, folded horizontally or vertically. When folded horizontally, such as in this video, the beginning and end will meet back onto themselves and loop, which you can see here, the purple sections connect. You can also fold it vertically, in which case the beginning and end are on opposite sides. The Hilbert totem, where the beginning and end meet in a closed loop, can be mirrored by its base to form a double lightsaber. Take a flat plane, wrap it into a tube, and wrap that tube into a ring, you get a toroid. Take a Hilbert totem, wrap it in a loop, and you'll get a Hilbert polyhedral toroid, where the beginning and end meet into a closed loop. There are two ways to divide a toroid. You can divide it by its equatorial circle or its meridian circle. This is a diagram of the Hilbert curve mapped to toroidal sixteenths, which would be meridian and equatorial fourths. The same diagram in black and white. Toroidal bicones are the central gap between two toroids. This form has a hyperbolic structure that can carry information along the toroid. And unlike regular bicones, the top and bottom can be open gaps rather than a closed point. This is a toroflux. Place it on a tube and it propels itself via gravity, carrying information toroidally from origin to destination. You can place multiple of them on a tube, and between them are toroidal biconical gaps. You can even loop information back to the beginning. The toroidal electron. An electron is a toroid of circulating electromagnetic energy that travels through a wire as current flows. In motion, it generates an electromagnetic field that surrounds and permeates the conductor, forming a continuous toroidal energy structure along the circuit. The same principle applies to electrical signals traveling through nerve or mycelial cells. Linear toroidal time. If we rotate a torus along a timeline, you can carry information in the biconical gaps from past to future. Hilbert cubes. Space-filling curves are 1D linear fractals that fill higher dimensional space. A Hilbert square fills the space of a 2D square. A Hilbert cube fills the space of a 3D cube. These are orders 1 through 3 Hilbert cubes. An order 1 Hilbert cube occupies a 2x2x2 grid. Each preceding order increases the grid's volumetric resolution by a factor of 8, subdividing every cube in the grid into a 2x2x2 subgrid. Hilbert cubes nest inside of each other without overlapping. When nesting, the central axes of each 2x2x2 cubic section are filled by the previous order. Here we have orders 1 and 2 nesting inside of each other, and orders 1, 2, and 3 nesting inside of each other. These are third-dimensional Hilbert curves. They're 1D lines that fill third-dimensional fractal space. In green is order 1, in blue is order 2, in purple is order 3. And you'll notice that order 1 doesn't ever touch order 2, and order 2 never touches order 3. They don't touch. And you can keep going on with the progression of orders. These will never touch as they fill cubic space. There's also another very fascinating thing about this. So if I go ahead and take the order 1 and scale it, you'll see that the order 2 Hilbert curve fits inside of it perfectly, like a nested helical structure that comes through both ends. A peek inside the tube. Hilbert cube expansions. A Hilbert cube minimum is a 1D line that has no depth. Thus it fills no space of the cubic grid. A Hilbert cube half expanded fills half the space of the cubic grid. And a Hilbert cube, maximum expanded, fills the entire space of the cubic grid. Half-expanded Hilbert cubes. When nesting, lower-order Hilbert curves fill gaps in higher-order curves by connecting central axes across each 2x2x2 section. When half-expanded Hilbert cubes nest inside each other, several of their corners and edges coincide. On the left, we have an order 1 Hilbert cube half-expanded, and on the right, we have orders 1 and 2 nesting inside of each other. This is an inside view, where the order 3 half-expanded Hilbert cube in green nests inside of an order 2 maximum expanded Hilbert cube in blue. The camera follows the path of the order 2 Hilbert cube. And here we have the negative of an order 2 half-expanded Hilbert cube. The Hilbert cube is in green, and the negative is in red, which has been mirrored at its base. Closed-loop Hilbert cubes. To form a looping curve, we multiply the order's cube count by 8, shrink the curve down to 1 over that total, and tile each curve to seamlessly connect along the 4 colored paths. An order 1 Hilbert cube fills 8 cubes. A looping order 1 Hilbert cube fills 8 times 8 cubes. The curve is shrunk to 1/64th the volumetric scale of the order 1 and then tiled along the 4 colors. An order 2 Hilbert cube fills 64 cubes. A looping order 2 Hilbert cube fills 64 times 8. And the curve is shrunk to 1/512th the volumetric scale and then tiled to the 4 colors. There are 2 connecting points at the beginning and 2 connecting points at the end of each looping Hilbert curve. A closed-loop Hilbert cube is a singular line or string of cubes that fills the space of a cubic grid. In red, we have the 2 beginnings and the 2 ends of each curve. These connect the curve into a singular strand that loops back onto itself. If we remove the red sections, we can form open looping Hilbert cubes, which allow us to continue tiling this structure. Hilbert time in the 3rd dimension. Every cube can represent a still frame of time. A 3D model can be placed in every cube with the slightest movement applied in every frame. If in the first frame a man picks up a glass, and in the second frame he drinks from that glass, and now in the 3rd frame he sets the glass down, we have an animation where movement is applied in every frame. A single cube can represent an entire 3D universe, and the next cube can represent the next frame of the universe. Thought experiments. Is time in our universe stored on a Hilbert cube, where higher order curves are finer resolutions of time? And is there a more efficient way to pack time? Hilbert cube, disks, and bicones. This is an equirectangular panorama of Hilbert cubes nesting inside of each other, orders 1 through 3. There are 2 ways to map a Hilbert cube to a disk, so that the beginning and end face outward, or so that the beginning and end face inward. A Hilbert cube disk, outside facing, fits inside of an inside facing Hilbert cube disk. We can balance that by taking two equal rectangular projections, stacking them on top of each other, connecting the beginnings and ends, and then warping them into a polar coordinates map. Now we have arrived at an equally balanced Hilbert cube bicone. This is an order 1 Hilbert cube bicone. It is composed of two order 1 Hilbert cubes, connected together by two lines. It is a singular line that completely fills the space of two cubes. Now let's take a look at an order 2 Hilbert cube bicone. Again, you have two order 2 Hilbert cubes that have been connected by two additional lines in the same direction, mind you, as the order 1 Hilbert cube lines, this horizontal direction. This is one continuous line that completely fills not one cubic space, but two cubic spaces, with internal nestings for finer resolutions. The Hilbert cube central viewer. In this animation, the camera stays stationary at the center of the grid and rotates to look at every corner of an order 1 Hilbert cube. The Hilbert cube central viewer branch fractal. A viewer in the center of the main cube may travel to any of the 8 surrounding cubic regions. Repeating this process through progressively higher order Hilbert cubes lets the viewer reach any moment or cell without having to follow the full curve sequence. This can be used to pack scenes of a 3D animation with general locality preserved when scaling a time factor. A recap of the presentation. Extraordinary discoveries made from Hilbert space explorations. New branch fractals in the second and third dimension, closing a curve to loop within the confines of its own grid in the second and third dimension. Linear Hilbert time in the second and third dimension. Efficiently navigating chronological datasets that preserve the proximity of events when scaled in the second and third dimension. Mapping radiation with bipyramids, keeping track of particle behavior over time using second-dimensional Hilbert cubes. Storing Hilbert curves on disks and extruding them into bicones to carry twice as much information in the second and third dimension. Transporting 2D information along a timeline using a toroidal structure, utilizing 2D Hilbert curves. Hilbert curves, an ivyOptic presentation. If you wish to request licensing or hire my skill set, you can contact me, ivyOptic@yahoo.com. If you have learned something new or enjoyed this presentation, please consider contributing to ivyOptic.com. Your contributions greatly help towards future research. Thank you. Slides marked with a red asterisk note content which belongs to other creators. Permissions have been granted for use.